Hello students, welcome to today's lecture on artificial neural networks. Uh, Till now we have discussed about uh, some basic concepts related to artificial neural networks in Unit 2, and then we have discussed about learning paradigms used in neural networks, and then we have discussed about the learning rules, the four types of learning rules we have discussed in our previous sessions. Today, we will discuss some more basic concepts related to the artificial neural networks from Unit 2 itself. So these two concepts are one is state space concepts related to neural networks, and the other one is optimization concepts related to neural networks. We'll see these two topics today, and this could be the last topic from your Unit 2. Okay, so let us start with an introduction to state space concepts. You might be knowing these concepts while you studied the design and analysis of algorithms, particularly in dynamic programming problems. While designing dynamic programming algorithms, you might have gone through these state space trees. Okay, so what is a state space search process? It's a process uh, in which successive configurations or states of a particular instance are considered with the intention of finding a goal state that satisfies a particular property. Okay. The problems that we tend to solve can be represented as a state space tree that consists of all possible solutions uh, regarding that particular problem. And then we can identify the solutions uh, that meets a particular criteria or goal states. We can identify the goal states from the state space tree uh, with the help of some criteria. Okay. Uh, Generally, a state space tree consists of all possible solutions. Some of them may not meet the particular criteria we are looking for. The goal state is the state which satisfies the criteria or which satisfies the desired property. Okay, so that is about state space tree. You already used this state space tree concepts in design analysis of algorithms. Try to recollect those concepts. And another point that we need to remember is state space search is not actually a traditional computer science search method, because representing the state space trees exactly in memory is not at all possible, since it occupies a lot of memory. Therefore, what is actually done to implement these state space trees is a state space graph uh, is generated uh, as and when the nodes are created, and the nodes are explored, and then if they are identified that they cannot move towards the goal state, then they can be discarded immediately. Okay, that means we can reduce the memory requirements by discarding the unnecessary nodes that are part of your state space graph. Okay, we can identify the unnecessary nodes by looking at whether that node can lead to the goal state or not. If it is not leading to the goal state, then we can immediately discard. That means from a space graph, only the nodes which are leading towards a goal state will be explored further. In that way, we can minimize the memory requirements also. Okay. Uh, and then the solution to any given problem, which is represented as a state space tree, may consist of goal state itself or a path from some initial state to goal state. So there may be a single solution for the problem, or they may exist more than one solution also. We'll see the examples later now. Um, State space is actually a set of descriptions or states where each such problem consists of one or more initial states. It is possible that you can start from anywhere from the states of the state space tree. And the second point we need to remember is a set of legal actions are the moves that are used to identify the goal state. For example, if you consider a puzzle problem, the general moves are moving the puzzle cubes towards left, right, up, and down. These are possible moves. And there may be one or more goal states also. Some algorithms identifies a single goal state, and some algorithms will try to identify all possible goal states also. Okay, depends on the algorithm that we apply. So the state space search can be formally represented as a tuple S, that is S comma A comma action of S comma the result of S comma A and cost of S comma A, where S is the set of all possible states, A is the set of possible actions related to a particular state, and action of S is the function that establishes which action is possible to perform in a particular state, in a certain state. The result of S comma A is the function that returns the state searched performing action A in state S. From state S, if we perform action A, what could be the result? That is result of S comma A. And finally, cost of S comma A is the cost of performing an action A in state S. Okay. Generally, this is going to be constant. It is assumed that this cost is going to be constant in state spaces, but in reality, it's not going to be true. Okay. So these are the mathematical representation or a formal representation of a state space search. Okay. Let us consider a simple problem to understand the state space concept. Water jug problem is a well-known artificial intelligence problem where two jugs will be provided, one with a capacity of 3 gallons of water and the other one with a capacity of 4 gallons of water. And there will be no measuring equipment available. The jugs also do not have any kind of marking on it. And the task is to fill the 4-gallon jug with exactly 2 gallons of water by using only these two jugs and without support of any other material. Okay, so initially both the jugs are going to be empty. So this is our water jug problem, and we need to identify what are the steps that are required to fill that 4-gallon jug with exactly 2 gallons of water with the help of that third 3-gallon jug. Okay, so let us assume that X denotes the state of 4-gallon jug and Y denotes the state of 3-gallon jug. And based on this, we can identify the production rules. These are going to be the production rules, all possible production rules here. We can make use of any of these production rules to quickly move towards the goal state, that is filling the 4-gallon jug for with 2 gallons. Okay, so let us identify the possible production rules over here. If the state is X comma Y, initial state is, and if this condition is met X less than 4, then you can fill the 4-gallon jug completely. It can be represented as 4 comma Y. X is replaced by 4 since it is filled with 4 gallons. Similarly, the same X comma Y, if Y is less than 3, if this condition is met, then you can fill that 3-gallon jug with 3 gallons of water. Then the final state becomes X comma 3. Similarly, if X is greater than 0, then it is possible that you can pour some water from the 4-gallon jug out of it. Okay, X minus D comma Y. If Y is greater than 0, you can perform the same action, X comma Y minus D. That means you can pour some water out of the 3-gallon jug. If X is greater than 0, then you can empty the 4-gallon jug. If Y is greater than 0, then you can empty the 3-gallon jug, the possible actions. If X plus Y is less than 7, then fill the first 4-gallon jug completely, and then pour some water from the 3-gallon jug to fill the 4-gallon jug. That means y minus 4 minus x. The remaining part is to be filled from 3-gallon jug. Similarly, if x plus y is less than 7, then you can pour some water from the 4-gallon jug to fill the 3-gallon jug. It is a possible action. If x plus y is less than 4, then pour all water from 3-gallon jug into the 4-gallon jug. That means x plus y comma 0. If x plus y is less than 0, then pour all water from 4-gallon jug to 3-gallon jug. That means 0 comma x plus y. So these are possible production rules. You may or may not utilize all these production rules to move to the goal state of filling the 4-gallon jug with 2 gallons of water. Let us identify a solution, a possible solution for the 4-gallon water jug problem. This is 4-gallon jug content and this is 3-gallon jug content. Initially, both are empty. The first step is fill the 3-gallon jug completely with the help of rule number 2. Okay, and then in third step, what we do is pour this 3 gallons of water into 4-gallon jug. Then it is filled with 3 gallons, right? Now this 3-gallon jug is empty. This is done with the help of rule number 9. And next step, again we fill the 3-gallon jug completely with the help of rule number 2. Okay. Now what we do is pour some water from 3-gallon jug into this 4-gallon jug in such a way that this jug is filled completely. Now there will be 2 gallons remain in the 3-gallon jug. Okay. Now empty this 4-gallon jug in 6th step. 2 gallons are there still in 3-gallon jug. Because we want these 2 gallons in 4-gallon jug, just pour this water into 4-gallon jug, empty it. Okay. So at the end of step 7, it is the goal state is reached, right? So this is a possible solution for the water jug problem. There may be other solutions also. This is one possible solution for the 4-gallon water jug problem. Okay, so you can identify other solutions also if you are interested. And this 7 steps will be the minimum number of steps required to fill a 4-gallon jug with 2 gallons. Similarly, we can see another problem here, 8 puzzle problem, where a 3x3 grid will be given with 8 square blocks labeled through 1 to 8, and 1 block will be left empty, a blank square. And the goal is to rearrange the blocks so that all the blocks are in order. So this is a puzzle problem. Suppose you are given with this initial state, some random initial state. You must move towards this final state, 1, 2, 3, 4, 5, 6, 7, 8. Okay, let us go through the steps required to identify that goal state. Initially, here is the empty location. So 1 is moved towards left. The move is move that black 1 towards left, and then 2 is moved up, and in the next iteration 5 is moved towards left. Okay, and finally you can get the solution by moving 6 upwards towards this position. So the legal moves are up, down, left, right. So with the help of 3 moves, 1, 2, 3, and 4, fourth move, with the help of 4 moves, we can reach this final state, that means goal state. Okay, so if you observe this solution, it is one possible solution among many. The state space tree can be used to represent all possible moves. It will represent all possible moves from the initial state, and you must be able to identify the states which reaches the goal state among all those possible moves. Okay, that is what the state space search helps us, right? So that is the first concept, space concept, which will be helpful in representing all possible solutions of a particular problem, and then identifying the goal states among all those uh, possible states. Okay. The next concept is optimization concept. We know the general meaning of optimization. It is something that the path or the way of performing a particular action effectively or efficiently. So that is called optimization. This effectively or efficiently, maybe in terms of the cost or time or something, whatever it is, it depends on the corresponding problem domain. Okay, so ultimately the optimization goal is to quickly identify an effective and efficient solution for a given problem. That is called optimization. So we can use a Hub-field network. Try to remember this name, Hub-field network, for this optimization purpose, for solving optimization problems. Okay, Hub-field network is actually a single layer containing one or more fully connected recurrent neurons. Therefore, because it is recurrent neurons, the feedback is given back to the original neurons, the output is given back to the neurons. Therefore, this kind of neural networks are useful for solving optimization problems. Okay, so when you are designing a Hub-field network for optimization problems, you need to remember these 3 points. The first thing is energy function must be minimum of the network, and the second point is the satisfactory solution rather than select one out of these stored patterns. So you must identify the satisfactory, that is effective solution. And the third point is quality of solution found by a Hub-field network depends significantly on the initial state of the network. So you must be careful enough to initialize the network to a proper state. Okay. Let us go through some examples. One well-known example that can be represented as a Hub-field network is traveling salesman problem, in which the aim is to find the shortest route traveled by a salesman by covering all the destinations exactly once and moving back to the starting point. Okay. You can see this in the example. Let us say there are 4 cities to be covered by the traveling salesman. I assume that we want to find out the shortest path starting from A, visiting all the remaining 3 cities and going back to A. Okay. All the remaining 3 must be covered only once. Only the first city which is visited will be revisited. Okay, so there are many ways to visit A to A by covering all the cities. We must be able to identify the shortest route. That is called the traveling salesman problem. So we can use Hub-field neural network to design this solution for traveling salesman problem. Okay. Uh, the matrix can be used to represent a TSP where if there are n cities, you can use n by n matrix for representing the costs of all those uh, visiting cities from one city to another city. Okay, from A to A, B to A, C to A, D to A, and then A to B, B to B, C to B, D to B, and so on. Even though it is given as zeros and ones, actually it is a cost adjacency matrix. It is going to be a cost adjacency matrix. And you can use the Hub-field network for traveling salesman problem. Every node in the network corresponds to one element in the matrix. Therefore, you require 4 by 4, that is 16 connections will be used in Hub-field network. Okay. So we'll go through this Hub-field network, how to design and how to identify the solution in the later chapters. As of now, just understand that the traveling salesman problem can be represented as an optimization problem, and the solution can be identified using Hub-field neural network. That point is enough at this moment. And another example is simulated annealing. It's a concept of uh, uh, motivated from solids. If we heat a metal above its melting point and cool it down, then the structural properties will depend on the rate of cooling. This is the main property. By using this point, we can use the same concept, simulated annealing concept, to solve optimization problems. Okay, in neural networks, what we can do is we can use that concept of simulated annealing for approximating the global optimization of a given function. Okay, or you can say it will be useful in training a neural network, right? And these are the steps used in simulated annealing. If you want to utilize this simulated annealing for training your neural network, the steps will be generate a random solution, and second step is calculate its cost using some cost function. Because this is a random solution, the cost is based on this random solution. And then try to generate a random neighboring solution, another possible solution, and calculate the cost of new solution with the same cost function which is used for calculating the cost of random solution. And then compare the cost of this new solution with that of old solution, as if cost of that new solution is less than cost of old solution, then move to the new solution. That means we consider it as the new solution will be considered, and again we continue the same process of identifying another neighboring solution and then comparing it with the new solution, and so on. This process will be continued until a stopping condition is met, or maximum number of iterations are reached. Okay, so this is how simulated annealing can be used in neural networks to solve optimization problems. There are other set of optimization techniques also. One solution is gradient descent technique. We'll discuss about this gradient descent technique in detail in fourth unit. Uh, I'll just introduce this technique over here. The main idea is we'll start with the initial guess of the solution, and then we'll calculate the gradient of the corresponding solution at that point, and then repeat the process by stepping the solution in the negative direction of the gradient. Okay, that means this gradient descent technique will move towards the final solution or the optimized solution in a quick manner. Okay, with very less number of steps. We'll see that later with the help of examples how it actually calculates the that gradients and moves towards the actual solution very quickly. Okay, this is how it works. Let us say this is the initial weight, and it will calculate some local minimum, moves towards, this is the minimum cost. Either way, if you initialize here, it will move towards like this. If you initialize here, it will move towards here. And sometimes it keeps like if the factors are not properly defined, that means the step size is not properly defined, uh, then sometimes it may be fluctuated. By starting here, uh, it can go back to this position, and then it can come back over here, and then it goes back, and so on. So it is always important to use a proper step size for identifying a quick solution. Okay, let us understand it mathematically. Suppose we have a function fx, and they're trying to find the minimum of this function. Then the steps will be get some initial value x0 for the x, and then calculate the gradient delta f of the function to find out the best direction to minimize it. Okay, now change the new value of x, that is calculate the new value of x as xn plus 1 is equals to xn minus theta into delta of f of x of n, f of xn. Okay, theta is actually the step size that I have told already. This is very important. If step size is not properly defined, Then the gradient descent takes a number of steps to move to the final solution. Okay. So estimating step size is going to be the most important factor here. Actually, a wrong step size theta may not reach convergence. That means it may not converge at all. The final solution may not be reached at all. Therefore, a careful selection of step size is very important. Okay, while choosing this step size, you need to remember these 2 points. Do not choose too large step size, or do not choose too small step size. You need to pick a moderate step size in order to converge quickly. Okay, and how to select this step size? These are possible options. You can choose a fixed step size for all the iterations, or you can choose different step sizes for every iteration based on the knowledge of previous iteration. Okay, so in either way you can use it. This choosing a different step size for every iteration will converge your neural network very quickly, right? So these are the two fundamental topics that I wanted to discuss today: the state space trees and optimization concepts. Maybe examination point of view, these may not be that important for you, but these two topics are very much important if you want to build complex neural networks in your research work or project works. Okay, so try to read these two concepts again. Try to understand the possible steps and uh, examples of these state space concepts and optimization concepts. And anyhow, we are going to make use of optimization concepts in fourth and fifth units. We'll discuss about this again in detail while designing the neural networks with the help of gradient descent technique. Okay, so that's all for today, and this is the end of second unit. Uh, I hope you understood the unit 2 topics well. Try to practice all the learning rules properly. Uh, 4 learning rules are very important for your examination point of view, and try to revise all these topics again. Okay, thank you all for your patient listening. When we come back, we'll start unit 3. Thank you all again.